Hello students, I hope you all have enjoyed my previous lectures. In relation, we have already read reflexive, symmetric, transitive and equivalence relation. Also, we have discussed about the equivalence class. Today, we will discuss about some facts on equivalence class and partition. A very important point. Partition. Yes. First, some facts on equivalence class. Number one. Right. If X is any set and F is an equivalence relation on X, then number one, each equivalence class is non-empty. That is, the equivalence class of is not null for all X belongs to X. Number two, if X for X, Y belongs to X, X, Y belongs to F implies equivalence class of X is equal to equivalence class of Y. Number three, two equivalence classes are either disjoint or equal. That is, for X, Y belongs to X, equivalence class of X is equal to equivalence class of Y, or equivalence class of X intersection equivalence class of Y is empty. Either they are disjoint or they are equal. Number four, union of all such equivalence classes is equal to X. Okay? If you want, we can prove it using the definition of equivalence class and equivalence relation. Let us try to prove this one. It's very simple. Prove. First one, if X is an element of capital X, then its equivalence class is non-empty. Suppose for X is an element of X, we have X belongs to F as F is what? Reflexive. F is reflexive. F is an equivalence relation, so it must be reflexive. So if X is an element of capital X, then X must be related to X. X must be related to x. So x is an element of, this implies x belongs to the equivalence class of x, right? X is related to x, so x must be in the equivalence class of x, and this implies equivalence class of x is non-empty. It is not empty. So from this we can conclude that no equivalence class is empty. Each equivalence class is non-empty. Each equivalence class is non-empty, right? Then second, for x, y belongs to x. If x is related to y, then equivalence class of x must be equal to equivalence class of y. Let us see how we will prove it. Okay. Yes, here you can. Yes, let me know. This is a set. This is another set. When two sets will be equal? If this one is the subset of this and this one is also the subset of this. Two sets will be equal if they are subsets of each other. So how we prove that one set is the subset of another? That means x belongs to one set implies x belongs to the other. That means, you see, x let z belongs to the equivalence class of x. Suppose this implies what? Z is related to x. From the definition of equivalence class, z is only eligible to be in the equivalence class of x. When it is related to x. So from this we can conclude that z is related to x because it is an element of the equivalence class of x, and this implies x now z is related to x and it is given that x is related to y. It is given. This is the hypothesis. If x is related to y, we have to show that this is equal to this. That means it is given to us. X is related to y. We have taken z in the equivalence class of x. We have taken z in the equivalence class of x. So z must be related to x. Now we have two elements. Z is related to x and x is related to y. This implies z is related to y. Why? As f is transitive. F is transitive. Equivalence class arises only when the relation is an equivalence relation. Yes, since f is an equivalence relation, it is reflexive, symmetric and transitive. So, since it is transitive, z is related to x, x is related to y, so z must be related to y. And this implies z is related to y means z is eligible now to be in the equivalence class of y, right? Now z is in the equivalence class of y. We have taken it in the equivalence class of x and we have seen that it is also in the equivalence class of y. So what conclusion we can take? Thus, z belongs to equivalence class of x implies z belongs to the equivalence class of y. Right? If it is in the equivalence class of x, then it must be in the equivalence class of y. And show equivalence class of x is a subset of equivalence class of y. Right? Now we are able to prove that this is a subset of this. Okay? Clear? Very simple. take an element Z in the equivalence class of X, and this implies Z is related to X. It is clear from the definition of equivalence class. Now Z is related to X, and by hypothesis X is related to Y. So Z must be related to Y. That means Z in the equivalence class of Y. So whenever Z is an element of equivalence class of X, it must be an element of equivalence class of Y. So that means this is a subset of this, because an element is here implies it is also here. So that means each and every element of this set is an element of this set. So it is a subset of that. And with similar argument we can show that equivalence class of Y is also a subset of equivalence class of X. It is left for you. You take an element W belongs to equivalence class of Y. Then using the same procedure, you can show that W is also an element of X. That means this will be a subset of this, right? Thus, it is a subset of this, and this is also a subset of this. Subset, maybe subset of this. So from these two, you can conclude that equivalence class of X is equal to equivalence class of Y. So when X is related to Y, equivalence class of X must be equal to equivalence class of Y, right? Okay, let us come to the third point, which is very important. Two equivalence classes are either disjoint or equal. That means there is no common point between two distinct equivalence classes. There is no common element between two different equivalence classes. Let us see. Okay. Do I put this part? Yes. Our third point is this: equivalence class of X, Y is null. Either equal or their intersection is null set. Okay. Suppose let equivalence class of X is not equal to equivalence class of this. So, we have to show that, we shall show that equivalence class of X intersection equivalence class of Y is null set. They are disjoint if they are either they are equal or disjoint. Suppose they are not equal, so we have to show that they are disjoint. Suppose, if possible, it is called the method of contradiction. If possible, let equivalence class of X intersection equivalence class of Y is not null. Suppose it is not null. That means there is an element Z belongs to equivalence class of X intersection equivalence class of Y. There is an element. Must. If it is not null, there is a common element. Say Z. This implies Z X belongs to F, and we will go another step, then it will happen. This implies Z belongs to equivalence class of X and Z belongs to equivalence class of Y. If it is in the intersection, then it must be here and it must be here. So, as it is here, what we can conclude? That Z is related to X and here Z is related to y, right, with the same relation. Okay, this implies two equivalence classes are either disjoint or equal, right? So this implies x z belongs to f and z y belongs to f. How? Because f is symmetry. F is symmetry, right? Zx belongs to f implies xz as f is symmetry because it is an equivalence relation. It is reflexive, symmetric, and transitive. This should be in our mind. So as f is symmetry, right? And this implies x is related to y. As f is what? Transitive, yes. As it is transitive. F is transitive. So x is related to z and z is related to y. So x must be related to y. Right? Now x is related to y. In the second point, we have proved that if x is related to y, then equivalence class of x is equal to equivalence class of y. This implies what? Equivalence class of x is equal to equivalence class of y. But this contradicts our hypothesis, our assumption. Let equivalence class of x is not equal to equivalence class of y. Suppose we have taken, we have assumed, but we have arrived at a contradiction. If this will not happen, then what will happen? We will arrive at a contradiction that equivalence class of x is equal to equivalence class of y. So, which is a contradiction to our assumption? Which is a contradiction to our assumption, right? So, what is correct? This is if possible let. That means it is impossible. It is not possible. It is not possible. Hence, equivalence class of x must be equivalence class of y. Their intersection must be null. Hence, equivalence class of y intersection equivalence class of x equivalence class of y must be null set. Means they are two disjoint sets, right? Okay. This is the main part, main property, main fact. Two equivalence classes are either disjoint or they are equal. Now the last one, the fourth one, union of such equivalence classes of x is equal to x. Yes, it is very simple. You see, fourth one is very simple. Yes. Because equivalence class of f is a subset of x for all x belongs to x. Equivalence class of x, it is what? It is the set of elements of x which are related to x. So it must be all the elements of this are here. So it is a subset of x for all x belongs to x. This is a subset. That means their union of such subsets must be a subset of x. If you take all the subsets of x, union of all the subsets of x, it must be a subset of x, right? Number one. Suppose this. Then again, now for x belongs to, again x belongs to x implies x belongs to the equivalence class of X. The equivalence class of X. Clear? Because the relation is reflexive. X is an element of X. So it must be related to itself. So it must be in the set, in the equivalence class of X, right? This implies X is a subset of union of these subsets. For all X, there is a equivalence class. So each element of these must be in some equivalence class of X. So this must be a subset of this. From these two, it is suppose B. From A and B, we have union of equivalence classes of X is equal to X, right? Okay. So this is all about your equivalence class. Let us switch over to partition. Yes, very important topic, partition. Partition is a common word which you know, but mathematically we do not know what is a partition. What is a partition? Most of the people do not know what is a partition. That is why quarreling among brothers, quarreling among countries always happening, right? Let us define what is a partition. Partition of a set. Let X be any set. Let X be any set. A collection P of subsets of X will be a collection P. Let us write down P equal to x1, x2, x3 up to xn. That means these of subsets of X will be a partition of the set X if number 1 Xi is not null for any I is equal to 1, 2, 3 up to n. Number 2, Xi intersection Xj is null set for I is not equal to j. That means these are all subsets of X, x1, x2, x3, xn, all are subsets of X. So first thing, each subset is non-empty. Each subset should be non-empty. Second point, two partitions are either equal or they are disjoint. That means xi, xj, when I is not equal to j, it is different from this, so they are completely disjoint. There is no common element. There is no common element between xi and xj. And number 3, union of such I is equal to 1 to n xi is equal to x. Clear? X is any set, P is a collection of subsets. Subsets, you know, subset. Yes, here x1, x2, x3, xn all are subsets of X. What type of subsets? Now, each subset is non-empty. Each subset is non-empty. There is no empty subset. Number 2. Two distinct subsets have no common element. Then number 3, union of these subsets is equal to X. So this is a partition. Let us take an example. Let us take an example so that it will be clear. Suppose let our X is equal to 1, 2, 3, 4, 5, 6, 7, this right? Let our P is equal to the set of subsets, say 1, 2, 3, 4, 5, 6, then 7, right? You see, suppose this is x1, this is x2, this is x3, this is x4. We have 4 subsets, and you see each subset is non-empty. First point, each subset should be non-empty. Yes, all of them are non-empty, and no two halves common element. x1, x2, there is no common element. x1, x3, no common element. x1, x4, no common element. Similarly, x2, x3, x2, x4, x3, x4, no two have any common element. And you see, union of all these 1, 2, 3, 4, 5, 6, 7 is equal to X. Right? Union of all these subsets, this union, this union, this. That means 1, 2, union, 3, union, 4, 5, 6, 4, 5, 6, sorry, 4, 5, 6, union 7 is equal to what? 1, 2, 3, 4, 5, 6, 7. So now it is X. So it satisfies all the 3 conditions of partition. So now this P is the partition. P, the collection of subsets of X. This is a partition of X. It is not unique. You may form different partitions. Suppose you can take 1, 2, 3, 4, 5, 6, 7 like this. But they should satisfy all these. Try to you do yourself. Try to form different partitions of the same set. Different partitions can be made. Now let us come to why we are reading here partition. Partition means, you see, suppose this is a set. This is a land. If you will divide it among 3 brothers, then suppose one brother will get this, another brother will get this one, another. You see, this is a smaller part, this is a larger than this. They may not be equal. Partition means there is no equality. They may be unequal, but they should be disjoint. That means there should not be any overlapping. There should not be any overlap. First thing, nobody should be debarred from his parental property. That means no subset is empty. Then there should not be any overlapping. Suppose this is a common land between, it is A, brother A, this is brother B, this is brother C. There is a common land. Yes, A claims that this is my land, B claims that this is my land. So this is a disputed land. This part is a disputed. Dispute is there. That means A claims that this is mine, B claims that this is mine. So it is not a partition. If there is, here A intersection B is not null, so it will not be a partition. So dispute will arise again in another case. When dispute will arise, if their union is not equal to X, suppose there is a undistributed parental property. Suppose here is a land which is, suppose it is A, it is for B, it is for B, it is for C. But their father has not distributed this property. So this is not a partition, because they will have controversy among themselves and a dispute, quarreling, whatever it may be, they will have if there is a common property which is not properly distributed their father. So this is also not a partition. So to be an partition, their union should be equal to X. They should be disjoint and each part should be non-empty. Right? Okay, three conditions. Partition should satisfy these three conditions. And you see, when an equivalence relation is defined on a set, when an equivalence relation is defined on a set, just before this partition we have read, no equivalence class is empty. First condition is satisfied. Two equivalence classes are either disjoint or they are equal. Second condition is satisfied. Either they are equal means same, or they are disjoint, completely different, and their union is equal to X. Clear? So this shows that we have already proved that the set of equivalence classes defined due to the equivalence relation forms a partition of a set. I can write down an equivalence relation partitions a set into disjoint equivalence classes. Partitions a set into disjoint equivalence classes. We have already proved an equivalence class is non-empty. Two equivalence classes are either disjoint or they are equal, and number 3, their union is equal to X. So they form a partition. Okay, so an equivalence relation partitions a set into disjoint equivalence classes. Okay, now second part, converse. Whether a partition defines an equivalence relation. If an equivalence relation partitions a set, then if there is a partition, is it forming a defining an equivalence relation? Let us see. Yes, a partition forms and defines an equivalence relation on a set, right? How? Let a partition of a set X of a set defines an equivalence relation on the set. How? I can show it. Suppose X is 1, 2, that example we have taken 1, 2, 3, 4, 5, 6, 7, right? Say our partition was this 1, 2, 3, 4, 5, 6, 7. Right? We have taken the partition. Let us define a relation, right? A relation f on x, but as f is equal to xy such that x and y belong to the same set of the partition, right? That means 1, 2 belongs to the same set, so 1 is related to 2 and 2 is also related to. You can show that f is an equivalence relation. F is an equivalence relation on x. Try to prove it yourself. Next time we will discuss this, but you try yourself. How? If this is the relation, how it will be an equivalence? You have to show that it is reflexive, symmetric and transitive. Okay? Do at your level. Okay? Of course, I want to tell you that if you have any doubt or you have any suggestion or you have any modification you want, then you can follow me through comment or through my Facebook account. Okay?